Welcome to the last part of Module 8, Module 8.5, where we're going to explore a little further the z-curve and how to find certain numbers that we're after. In this case, boundary values, which are values along the x-axis, if we know an area or a probability. So in the last section, we looked at using the z-table to find areas or probabilities. In this section, we're going to use the same z-table. First, we're going to look at it from the z-table perspective, then we're going to look at it from a technology perspective, but using it in reverse. For example, this is helpful when we want to find boundaries of the curve that correspond to a given probability or a given percent of the population. For example, what z-value would have an area of about 3%, or specifically 0.0301 to its left? To do that, we would turn to the body of the table until we find the closest area. And in this case, the closest area is actually the exact area, 0.0301. This would be the area to the left of the z-value that corresponds to negative 1.8 and then 8 in the hundredths place. So we would have to go negative 1.88 units or standard deviations to the left of 0 to have about 3% in our left-hand tail. Example 2, if we want to find the z-value that has an area of 0.065 or 6.5% to its left, we would go to our table until we come as close as we can to 0.065, and here we see our eyes are kind of drawn to the 0.065 and then with an extra 5 there in the thousandth spot. Notice though that for 0.065 has a 0 in the hundredth spot. Because we don't have anything written there, we assume it's a 0. So this is not exactly the value that we were after, but this is the one we probably first noticed. If we go to the left of that, we can see that this one is also pretty close to 0.065, but it's off by 7 1,000 or 10,000ths, where this one's off by only 5 10,000ths. So if we were only using the z-table, we would probably go with this one because it's the closest, and we would just estimate it to be negative 1.51. In general, the z-table is very limited in this regard. It can only give us areas for z-scores rounded to the nearest hundredth. That's as far as our top columns go. And so therefore, for most calculations, we're going to use technology, which we'll use here in a second. All right, but for certain ones, like here in this example, we're looking for 0.0250 to its right. There's two ways we can accomplish this with the z-table. Number one, we can calculate the complement. Since we know the z-table is always going to the left, if I find the complement of 0.0250, the complement of that would be 0.9750. So in other words, here's our z-table, here's the z-value we're after. We don't know what that is, but we're told that it has 0.0250 to its right, and so we know that corresponds to 0.9750 over here to the left, which is where we would turn to the z-table and look up 0.9750, and we see that it corresponds to exactly 1.96. You might recall that when we talked about, well, actually I'm not going to get into that right now. The other way we could have done it is to know that our bell curve is symmetric. And so we could look up the corresponding negative z-value, knowing that the one we're actually after is going to be positive. So if we look up in the table 0.0250, we find it right here. 0.0250, we see that corresponds to negative 1.96. But of course, since we know symmetry, that would correspond to a positive number on the right, having a about 2.5 to its right. So we could always use the symmetry of our normal curve, and this applies when we're talking about our calculators as well. We can use that property of symmetry to find the z-values. But now let's look really at what we're going to mostly use, which is technology, to find our z-values. So you want to think of the z-values as boundary values more in general, because sometimes we're actually be looking for x values, which are data values, not just z-values. So let's leave with an example. We want to find the z-value that has 0.065 to its left, as we saw previously. In your calculators, you want to enter second vars, so it's under the same menu that normal CDF is, but it's the one right underneath it, choice number 3, invert norm. You can kind of think of that as inverse. We're using the table in reverse. 3 things to enter in here. The first thing is the area to the left. Invert norm only understands that you want an area to the left of the boundary value you're after, just like the z table. Then we want to enter the mean. If we're looking for z-values, of course the mean is always 0. And then we want to enter the standard deviation, and for z-values, the standard deviation is always 1. So for this problem, we put 0.065, 0, 1. We can see more specifically that it was negative 1.5, not just negative 1.51, but negative 1.514. So that's the more specific answer, the more exact z. On our table, we can only go as far as negative 1.51. And we see that's why, is that really there should be a 4 on the end of that. It's important to remember that the first number is always the area to the left of whatever value you're after, even if what you're given is an area to the right. So if you're given an area to the right or a probability that is greater than or to the right, then you need to find its complement. So here's an interesting problem. Find the z, or the value of z, such that the area to the left of negative z plus the area to the right of positive z is 0.10 or 10%. This tells me that I'm being given the sum of 2 tail values. Right? And so the sum of this tail plus the area of this tail is equal to 10%. That means that there is 5% or 0.05 in each tail. And that's necessary because, again, the calculator only understands area to the left. So if I divide that up evenly, 10%, leaves 5% in each tail. And so that 5% is what we want to pursue if we're pursuing the value that's on the left. Doesn't matter which one we choose, but if we pursue the value on the left, we would put invert norm 0.05, 0, 1, and that gives us the z-value that has 5% to its left, negative 1.645. If I'm after the value or the z that's on the right, we would input 0.95, right? 5% to the left. That means if we go backwards to the left, that would be 95%. We're throwing in 90% between here and here, and then another 5% to the back. So we get, again, positive 1.645. Notice that that relationship of symmetry would only leave us with only having to find one of these, and then just changing the sign for the other one. All right, what z-value has an area of 0.8888 to its left? Go ahead and use the technology to see if you can find that value. I'm going to put all of these up here. We're going to use technology. You can pause it at this point. See if you can calculate these. All right, and if you used invert norm to find these values, 88.88% to the left corresponds to a z-value of 1.22. For a z-value that has an area of 3% to its right, we understand that means 97% to its left, so we use invert norm 0.97, 0, 1. and we get 1.88. If you use the 3%, you would have got negative 1.88, which is the right number but the wrong sign, since we're asking for 3% to the right. And then what about having an area of 95% between them? Well, in this case, having 95% in between them means that that 95% is in the middle. That leaves 2.5% in each tail. And so when we calculate it, we're either going to go for the negative or the positive, just as we did on the last slide, with 0.025 if we go to the left, or 0.975 if we're on the right. And that gives me 1.96. Now here's an interesting question. What z-value represents the 95th percentile, meaning that 95% is to the left? Well, if we put in 0.95, that leaves 95% to the left, which would be 5% to its right. We see that that one that we found earlier, 1.645, is the z-value that represents the boundary between 95% on the left and 5% on the right. Let's take this into some actual numbers now, because we can use invert norm not just for z-values, but also for data values or x values. And here we're going back to the body temperature examples that we're using. If we wanted to know what the actual body temperature would be, that would represent the 95th percentile, meaning 95% of the body temperatures will be less than this value and 5% will be greater than this value. That means 95% is on the left. I'm going to draw a little picture here. But here we're told the actual mean and standard deviation of the given data set. So we put in 0.95, area to the left, 95%, our mean and our standard deviation, and we get 99.8. So what we can conclude with this is that 95% of the time, if we select a random person, your temperature is going to be less than 99.8 degrees, and only 5% of the time will it be greater than that. Here's another situation. See if you can calculate this on your own. The weights of college females are normally distributed with a mean of 150 pounds and a standard deviation of 20 pounds. What weights represent the boundaries for 95% of the population? In other words, this is a two-tailed situation, and we want 95% in the middle. We want to know what the lower boundary is and the upper boundary is for that middle 95%. This means we're leaving 2.5% in one tail, 2.5% in the other tail. And so use your calculators to come up with that. You'll find that the boundary values are 110.8 pounds and 189.2 pounds. 95% of women then, according to these numbers that we've used, would fall between 110.8 pounds and 189.2 pounds. The number of cell phone minutes used by students at one university are normally distributed with a mean of 110 minutes and a standard deviation of 33. What is the third quartile value for cell phone usage? If you remember, quartiles represent quarters, so the third quartile would be the equivalent of the 75th percentile, meaning 75% are to the left, 25% are to the right. See if you can use your calculators to come up with this value. And this value is 132.11 minutes. That is the end of this last part of Module 8.